All right, so we're going to do a little experiment. And one of the things that I really like about this class, we're talking about all these technologies and all this engineering. Many of these technologies are ancient, right? People, famously the Romans were making cement, or we call it Roman cement. And, as we just talked about, the process of essentially kilning limestone at high enough temperatures. So remember, limestone is made out of calcium carbonate. We've been talking about that for a while. And the process of creating cement with it, like taking that limestone and making it something really useful, we have to create enough energy that actually one molecule of CO2 is driven off, and the product that we're left with is calcium oxide, also known as lime. The technology to do this is not very technological. It's essentially fire, right? As with most of these old technologies. So what I have here is some limestone. I grabbed a few pieces. Limestone can have lots of different appearances. This is kind of typical what we would call micritic or fine grained limestone, which is essentially that calcium carbonate mud. Oftentimes it has big fossils in it and things. One of these pieces might have a few fossils in them, maybe a piece or two, but nothing significant. So what we have here is just generally fine-grained limestone, and we're going to cook it. So we're going to take this stuff and we're going to kiln it at about 1,000 degrees Celsius, and then we'll have to let them cool off, and then I'll bring them back out of the furnace, and we'll kind of see what we can do once we've created these kind of lumps of calcium oxide or lime. We'll add some water and we'll kind of see where we go from there. All right, so the next thing we need to do is to get these bad boys into the furnace. All right, so I've switched over to the lab. I actually have our little muffle furnace here. It's a furnace that's capable of getting up to the temperatures we need. I've got my little ceramic plate, set my chunks of limestone. I didn't break them down, and they have some whiteout on them because I was using them for my geology courses. But I'm going to go ahead and start up the kiln, and we'll just put these bad boys in there and see how it goes. All right, so this is our little furnace. I'm going to pop this thing open. Like I said, we've got this heat-safe plate, our limestone with a little bit of whiteout on it. And I have it in this fume hood because, well, it will give off gas, right? So it's going to give off CO2 gas. One of the things that we have talked about is that actually the production of concrete is one of the, kind of in and of itself, is a pretty significant source of atmospheric CO2. Sadly, we're gonna make a little bit of CO2 here, but it's contained in this fume hood, so it won't be in the building. So I'm going to go ahead and close that up. I'm going to hopefully remember how to drive this thing. So the first step is power on. I gotta set the temperature. It looks like, look at that, the temperature is set to 1,000 degrees Celsius, and I'm gonna just go and do some other work and come back, and hopefully we'll see how it worked out. So we're going to be talking about concrete in this module, and concrete is a super important building material, right? We use it for everything, right? We buy it at Home Depot, mix up bags of concrete, but it's actually a technology that's been around for a really long time, right? The Romans kind of had invented what we call Roman cement and used it for brick, mortar between bricks and things. Prior to that, bricks were stacked essentially dry. But before we get to kind of the ultimate process, I want to remind us how limestone forms. We met this again back in the sedimentary rocks lecture. But essentially in places where there's a few conditions that have to be met. So the water has to be warm and fairly clear, meaning Further from a continent is better, because you don't have all of the sediment kind of sloughing off of the continent. Essentially, what you have in those conditions is an environment that's really suitable for marine life, especially planktonic marine life. So you have all sorts of little critters, living in the water. Some of them might be kind of building reef, sorts of environments. And what happens in that case is all of those little creatures are actually pulling CO2 out of seawater, mixing it with carbon, and using that to create their shells. So the shells are technically made out of a mineral called aragonite, but aragonite is a type of calcite, which if you take a chemistry class, you'd recognize as calcium carbonate. So calcite or aragonite is the mineral that these shells are made out of. And ultimately, these creatures die. And what happens over time is that calcium carbonate will dissolve back into the seawater. So we'll get, higher percentages of calcium carbonate in the seawater. But it turns out that this isn't true for the entire ocean. So at higher temperatures but fairly low pressures, the calcium carbonate is reasonably soluble, right? The water can hold a reasonable amount of calcium carbonate, but not tons, right? Because it's really kind of one of the things that's most tied to is pressure. So we have this water and it's kind of littered with calcium carbonate, but as that concentration of calcium carbonate starts to reach essentially the level of saturation, the amount that can be handled in this seawater, once you surpass that, it actually starts to crystallize out of the seawater. And so it forms these little tiny crystals of calcite. And, they're much too small to see. Essentially they look like mud, right? If you're to think about how big is a particle of mud, well, they're really small, like in the, a couple of microns in diameter. And so we get this calcic mud that starts piling up on the bottom of the ocean. But what I drew here, I actually drew another line, so there's actually a depth that's roughly 2 miles. Kind of average depth for the ocean is maybe 3 to 4 miles. Below about 2 miles in depth, the solubility, because the pressures go up, the solubility is dramatically increased, and that means that water can hold far more CO2 without it precipitating out. So we don't tend to get limestone formed in the deep ocean. It generally forms on places that are, well, first of all, warm, but shallow, in places that we call the continental shelf environment. And that doesn't make up too much of the ocean, right? That's, 5 or 10% of the ocean basin is what we would consider continental shelf, maybe about a mile deep or something. But that's really what we think of as the limestone factory, places where lots of these critters are living, they're dying, they're dissolving, and then as the concentrations reach kind of the limit of solubility, they start to crystallize out and form this mud. So this mud, that's what we're interested in. And the mud has the same composition. It's the mineral calcite, the same thing that those little critters are pulling out of seawater and concentrating into their shell. So over time, these little tiny crystals of calcium carbonate, of CaCO3, will actually begin to grow and interconnect with one another, and they make a solid rock. And that's the rock that we call limestone. And because of that, limestone is often filled with fossils of things that didn't dissolve, whatever landed here. So, there's oftentimes fossils of corals and, crinoids and brachiopods and bivalves and all sorts of things. Limestone is famously filled with fossils. So here I've drawn an outcrop, or I guess kind of a cross-section view. This symbol, this kind of brick pattern, that's the universal symbol for limestone. And what we're going to do in this case is we're actually just going to collect that limestone, so there's no one part of it that's more valuable than the other. And we're going to have a rock that is nearly 100% calcium carbonate. Turns out it's not 100% calcium carbonate usually. Usually, there's some percentage of mud, clays, other things that kind of could get into that depositional environment. So it's not just the dissolved things; it's sediment that was sloughing off of the continent. So we definitely have different grades of limestone. But fundamentally, what we want to do at this point, if we're going to take this rock and make it do this cool thing for us, right, to make cement, we have to modify its chemistry a little bit. So we can come in here with some heavy machinery. We'll get rid of all of this overburden because we don't want that. We'll go in and, we'll scoop out our limestone that we're so interested in. And we can take that limestone and process it. And actually, this is something that you've probably seen, maybe out near Durkee, Oregon, as we kind of drive, out of Boise into Oregon on the way to ultimately Portland, I guess. You drive through this narrow canyon, you actually see the ruins of an old limestone plant or an old concrete factory. And then Ash Grove Concrete is, like I said, near Durkee, Oregon. And essentially, they are mining limestone. So you can take a quick look. This is a snippet from Google Earth, and you can see that they're just mining limestone. This, in this case, is called the Weatherby Formation. And they take that limestone, they move it through a series of conveyor belts, ultimately down to their factory, where one of the first things they do is they kiln that stuff. And so let's talk about what happens during the kilning process. So I've drawn a cartoon of a kiln, and we're kilning one chunk of calcium carbonate limestone, right? We went and collected from the Weatherby Formation, or from Mackay, Idaho, or anywhere you have limestone. And what happens at that point is when we kiln this to about 1,000 degrees, we've then created enough energy to drive off CO2. And we've talked about CO2 a lot, and that's kind of what we're dealing with here. And one of the things when we start looking at global CO2, one of the kind of point source locations of CO2, aside from generating power, like in coal, natural gas, or oil for transportation, the production of concrete is also a significant source of CO2. And we're kind of seeing that process here. So once we've done our process, we've now actually changed the chemistry of our starting sample, and rather than it being calcium carbonate, CaCO3, it's actually calcium oxide. That's kind of what's left behind in that case. And here, this is highly reactive, essentially a product called lime. And at this point, we could process this and we'd get a product that's called slacked lime. We're going to do a demo. I'm going to show you kind of a few of these steps. But to get to real concrete, we need to have some other additives. And again, this is a little bit kind of magical, right? So these are the limestone that crops out near the town of Portland in England, not Portland, Oregon, or Portland, Maine, but Portland, England, OG Portland, if you will. That tends to have the right kind of other stuff, if that makes sense. So it turns out there's a certain type of clay that needs to be there in a concentration of about 10%. There are a few other things that need to be kilned with this lime to make it so that when you mix it with water, it will react and solidify. So we don't necessarily have those ingredients here. Oftentimes, concrete factories will be doing this process, recovering lime, but they'll actually buy those materials on the market, mix them with their raw ingredient, kiln the whole thing together, and then at the end you have this powdered material that acts as a cement. One of the things to keep in mind is the difference between cement and concrete. There's different ways to strengthen it. Generally what we do in making concrete, like if you were to have a concrete slab poured, we take the cement, right? That's the cementing agent, the magical kind of chemical combination that we made here, and we mix it with sand and gravel to not only lend it strength, but actually add to its volume. So we take the lime, we mix it with sand and gravel, we slurry that with water, and then it's kind of activated and ready to go out to the job site. So one of the things we had talked about prior is that we have quite a few kind of gravel companies here in the local area, and they collect aggregate, right? So gravel and sand, and they separate it by grain size. A lot of those companies that make aggregate, they essentially will buy this magical powder, potentially produced out in the facility out in Durkee, Oregon, and then they take that, bring it to their gravel pit, mix it with aggregate, mix it with sand and gravel, and put the slurry in, pack it up in a big drum on a truck, spin it around, and send that out to the job site. So the process of getting from limestone to concrete, just to kind of reiterate, first of all, we talked about the depositional environment of limestone. That has to be uplifted and kind of crops out, and we go and recover it. We then kiln it. If it doesn't have the right impurities, right? Remember we talked about the clay content and the sand content and some other things. We can add those as needed if our local limestone doesn't have that. And we kiln it. At that point, we can process it into a powder, essentially hydrate it with water. And then we can add other materials, gravel and sand and things like that, aggregate, to make the concrete, and then again send that out to the job site. So the steps are not very difficult, and the technology, like I said, something that we've been doing for a long time. Right? The Romans were doing this. Roman cement is still a little bit of a mystery because no one wrote down the kind of perfect recipe for it. It turns out one of the secrets was using salt water. Who knows? But that's kind of for a different time. But as we've kind of finished this discussion, I'm going to give you guys a demo where we take some limestone and at least do the first part of this process and kind of see how that goes.